let's go ahead and... So funny story. So funny story. This first example that I went over, this first example about Monte Carlo methods that I went over. Funny story. This is the one I use on the exam, so I'm going to have to find a new exam question. So if you're wondering the level of difficulty that Monte Carlo is going to be on the exam, it's around this level of difficulty, what we went over, which was our first example, which I introduced because it's a fairly standard, fairly simple example. Okay? So just keep that in mind. Now, we have a couple of different days. Let me go ahead and mute the me on the bottom so I can pull up the calendar over here. So the idea here is that 29th I will go over, most likely I'll end up going over some kind of brainstorming stuff, I suspect, for the final project. I'll introduce the final project and the ideas on the 29th. Because guess what? We're pretty much done with the curriculum. Kind of, sort of, but enough that believe it or not, you know enough programming now to be, I guess, dangerous at it. The entire point of this final project, by the way, is to toss you into the deep end of the pool and make you realize that in fact you did learn how to swim, as hard as that is to believe. And you know, you're not, and so I will be going over kind of the different ideas that you might have for a final project on the 29th. On the 31st, I'm going to review the exam. Okay? The exam will take place in your week 11 labs, which means it will be starting on the 5th, 6th, 5th, 6th, 8th, and then the following November, which would be November 11. So the exam will be in 2 weeks. It will be in 2 weeks, but that doesn't include the 4th because the Monday lab is lagging. Remember? That makes sense to everybody? Furthermore, I want to try to target proposal day for the 7th because that would give you basically a full month to work on the final project, because that final project would be due on December 9th, which is the latest I can make it due, right? Because that's the final day of classes. Make sense to everybody? So, but you're going to have time to think on it, okay? So I'm just letting you know what's coming up. After the last two homeworks are the Hawaiian pronunciation lab and the PIG assignment. I'll be going over the PIG assignment or parts of it in no later than November 5th. Probably after I do my exam review. Now, the big thing about the PIG assignment, and the reason that I figured out why Canvas auto-imported them to be this late. Because typically what happens is I make Hawaiian do today, and PIG do on November 1st-ish. But I generally have to give extensions to that, so it's imported the extension. So congrats, the extensions have automatically been granted for those. So we will, but PIG is worthwhile looking over for Monte Carlo because it does involve 2 Monte Carlo approximations as part of it. Also, you should have received a practice exam. The exam is basically 3 parts, which is file reading, function writing, and a Monte Carlo approximation. The Monte Carlo approximations I have on the practice exam are going to be more difficult than what I have in mind for the, on the practice exam, it's more difficult than what I have in mind for the actual exam. That is the way I like to do it. I like to make the practice exam harder. Okay? Once again, you will be, Gesundheit. You will be allowed a cheat sheet front and back, again. Because, again, it's not open note, because I believe that part of being able to, the important thing about being able to reference information is knowing what you'll need to reference, and that helps you prepare for that. Okay, So with that in mind, let's go ahead and get my face back on here on the recording. And what we're going to do is we're going to open up my whiteboard to review the problem I left us with. We're going to go over this problem, and then we'll do the problem in the problem on Runestone, which is the Monte Hall problem, which I think is great because we're doing Monte Carlo, but those are two differently spelled Montes, which is funny to me because I'm easily amused, I guess. Okay. So to review this problem, okay, we have this problem that we have these black cards and white cards, okay? So we are given 5 black cards and 2 red cards, okay? And the game that's being presented to you as follows. The game is, I want to flip over 3 black cards without flipping over a single red card, right? Black cards being clubs and spades, red cards being diamonds and hearts, in case you're wondering where black and red are coming from there, right? So you can try this with a normal deck of cards. I'm sure at least one of you tried it at home. So, and basically I'm saying if you're able to do that, you get $1, and but if you aren't, I get $1. So if you win, you get $1. If you lose, you lose $1. Now, the person who's trying to scam you, because this is a scam, will basically say, okay, well, the first card you flip over, you have a 5 out of 7 chance of getting that correct. Everybody agrees with that. That is not the lie here. The first card you flip over, you have a 5 in 7 chance of getting that correct. Okay? Once we flip over one black card, the next card has a 4 in 6 chance of being correct, right? The second card has a 4 in 6 chance of getting correct. And then finally, the last card, when we have 5 cards left, 3 of them are black, 2 of them are red, so we have a 3 and 5. This is completely true. This is not the lie. The lie is the next part where I said, okay, so the first one, this is greater than a half, this is greater than a half chance. This is greater than 1/2, right? That's 2/3. And this is greater than half. So your chances of winning have got to be greater than a half because all those 3 of those are greater than a half. That's the lie there. Because it sounds nifty. It sounds plausible. But if you study statistics, you know that what is this? These are dependent probabilities. These are dependent on each other, meaning that these aren't independent flips of the coin. You can only go to the second step if you've gotten the first step correct. You can only go over to the third step if you've gotten the first 2 correct, right? So these are not independent. These are dependent on each other. So the way you calculate the actual odds of getting this is you multiply these. That's how it is done in statistics. You multiply these. It would be whatever this fraction is, which is, let's see, 5 times 4 is 20, times 3 is 60, right? Over 5 times 6 times 7. Well, 5 times 6, I don't remember off the top of my head, but 6 times 5, hey, we know that, that's 30. 30 times 7, that's 2100, right? And now cancel out those zeros, right? And now pull out a 3, right? So divide both sides by 3. So that becomes a 2 out of 7. So your chances of winning, according to this, are 2 in 7, right? Did I mess up on the math there? That wasn't a lie. I just kind of was doing it off the top of my head. Yeah. Okay. Hopefully I didn't mess up on the math, but hey, you might not, but the point being is you don't know statistics. Why should you? You haven't taken that class. That's like 2,000, 3,000 level, depending on what major you are. So what are we going to do instead? We're going to simulate the game. We're going to simulate this game and play it instead. We're going to make the computer play it, and we're going to just see how this goes out. Now, one thing we're going to do to simplify the simulation is that because the cards are flipped over and they get shuffled, picking one card is basically the same as picking any other card, right? Doesn't matter which card we pick. So if it doesn't matter what card we actually pick to flip over, which card we choose to flip over, since all of them have an equal probability of being good or bad, or rather, they're as equal as any other to be good or bad. Since it doesn't matter which one I'm going to flip, to keep it simple, I'm just going to flip over the first 3 cards each time, okay? Since that will be shuffled. And that's going to make it a lot easier to calculate for us. Make sense? So again, how do we do this? Well, we're going to go ahead and set up a new, I'm going to set up a new Python file. I'm going to go ahead and create a Monte2 a file called Monte2. Now, guess what happens if you forget to import a random on an exam, by the way, because the first thing we need to do here is import random. Guess what happens if you forget to import random? You completely fail the class, get a 0 in everything. No, of course not. I'm not even going to notice. Not even going to notice. Don't worry. If you forget to import random on the exam, don't even worry about it. That's not what I'm testing. Right? If you forget to import random, it's going to tell you, oh, you didn't import random, and then you fix it. Like, that's what's going to happen in real life. So, oh no. I'm not interested in gotchas like that. That is not what I'm looking for. Okay? If you do take a look at the exam, hopefully the practice exam should have some questions with rubrics on them, but every question on the actual exam will have a rubric, a point-by-point breakdown of what I am looking for, that both you will be able to see and use as a guide to solving the problem, but also so the TAs will be able to grade consistently. So the first thing we do for all Monte Carlo problems is we import random, okay? Because we need to be able to do some kind of randomness, okay? So the next thing I need to do is I need to generate, let's call it a deck, or we're going to generate our cards, okay? So def generate cards, okay? And what I'm going to do, this could be done as part of the game itself, right? You could also call this setup because it sets up the game. You could do this, this method isn't strictly necessary. You could put this in the game method that we're going to write itself, the method to play the game. But honestly, I just kind of want to break it down so I can test this. Make sense? I want to make it so it's easy to test right now. Okay, so I'm going to generate these cards. Specifically what I'm going to do, my goal here is that I want 7 cards, right? 5 black and 2 red, and then I want it to be shuffled up. Make sense? I want a random sequence that has 5 black and 2 red. So how do I do this? Well, I'm going to make it easy for myself. I'm going to go ahead and say my cards are equal to a, so there's a couple different ways to do this. Cards are equal to a list. And the first thing I could do is that if you forget about how to specially use Python's list, concatenation, replication kind of thing, then you could just do it like this. For in range 2, we want to do this twice, cards dot append, and I'll just use B for black, right? Oh, sorry. Actually red there because we want 2 reds, right? And then copy paste this, and then we want 5 black, right? And that gives us 2 reds and 5 blacks, right? Make sense? And then finally, what we do is to make this a random sequence, is that we would do, we would say, let's see, random dot shuffle. And I just got to check for shuffle. Okay, I love it when it pops up with the documentation I need. It says shuffle list X in place and return none. So that means that basically that it will take what it is and it will actually change the list up, as opposed to generating a new list. So random.shuffle, let's see, random.shuffle, and then what are we going to shuffle? We're going to shuffle the cards. Make sense? Random.shuffle cards.
I have a question.
Yep.
When you're making multiple for loops, like I usually use the I variable as like for blank, but like will for blank get it working anyways?
Yes.
So
I use blank to be very explicit that I'm just doing this for loop as a form of repetition to repeat X number of times. That I don't care about what this variable is. I don't care that it's changing. Make sense?
yeah.
So either way works though, because I didn't start using this for forever, but also it's perfectly fine to do this.
I was going to ask more also, like, does it matter if you keep repeating the same variable?
Not really, no. Doesn't really matter. I mean, this is also isn't the way I like doing it. I prefer doing it in the one-liner for Python, but I'm going to show that after I show this method. Okay, and then we're going to return cards. So we created our cards, we shuffled the cards, and now we can play with them, right? So what I'm going to do is I'm going to test this out, and I'm going to say print gen cards. So that function, this verb, generates 7 cards for us. Run module, save, and we get red, 5 blacks, followed by a red. Let's go ahead and just see. Gonna just scoot that over here so we can keep running this. So, and as you can see, the reds end up in random places because that's what shuffle does. Make sense? So it's complete. Yes.
Does it always make the 2 reds together next to each other?
Does it always? Not necessarily.
Oh, okay. I see.
Not necessarily. We just got a couple of interesting cases. That's all.
Okay.
That's randomness for you. It sometimes produces results that don't seem random. Because that's just what happens. All right. Now the other way to generate this, rather than using these 1, 2, 3, 4, 5 lines over here, is to just use one line and take advantage of what we know about Python, right? Specifically, the one line would look like this. So it would look like cards is equal to a list, right? You could just simply write this out, right? It just takes a while. You could do this, right? You could manually have written out like 5 blacks and 2 reds. Make sense? But why do that when we can just use this when I can remind you that this notation exists? So multiplying takes an order of operation first. Multiplication here is a replication operation, which means, hey, I want 5 of those B's and I want 2 of those R's. Oh, and then concatenate those together. Make sense? Yes? Could I do that inside the brackets? If I did this, so if I did it like this, I'd get a single string with 5 B's, which might work, but I prefer to keep this as a list right now, rather than a string. But yeah, it's just a different way of doing stuff like that. All right. So now that we've got a game set up, we can play the game. So let's go ahead and write a game method. So def game. Okay? And what we'll do is that we're going to return for this game, it's going to be fair. You're going to see this is a fairly short method. Okay? What we're going to do is that we are going to simply return true if we win and false if we lose, right? Because right now, I don't care about the statistics of individual outcomes. What I care about is how often I win versus how often I lose. Make sense? So first thing I need to do is cards is equal to gen cards to get what I'm going to be using. The next thing I am going to do is what? I need to pick 3 cards. Now, I could pick them at random, right? I mentioned that I'm not going to do that, but I could if I knew the method. I think what? Choose? Random, not choices, probably, or random, not choose. I'd have to look at what the difference is. But overall, the point is that you want to choose without putting it back. And I forget which one does that. Choose. Turn case size list of population of elements. So choices might do it. But let's go ahead and let's go ahead and go on a bit of a goose chase. Random Python. If I can spell it, okay, it says, warning, pseudo-random generators in this module should not be used for security. For security or cryptographic uses of random stuff, use secrets. it says, see also, if you're interested in the method as to how random numbers are generated, you can look up Matsumoto's and Nishimura's Mersenne Twister, a 623 dimensionally equidistributed uniform pseudo-random number generator, published in 1998. So, anyway, let's go ahead and look at random.choice. Chooses a random element. Returns a k-side list from population with replacement, meaning that we would choose something and we'd put it back, meaning we could choose the same card. We could flip over. If we did this, it means we could say we flipped over the same card multiple times. That's what with replacement means. We want it without replacement. So without, so yep, sample, that's what it is. Return a list of k unique elements chosen from the sequence. So used for random sampling without replacement. Okay, so we're just going to keep that in the back pocket right now. I'll show it to you later. Okay, I'm going to just simply comment this out, but I'm going to return to this because what did I say my strategy was going to be? I said since it doesn't matter which 3 cards we flip over, I'm always going to flip over the first 3. Right? I said that, right? To make it simple. But for those of you who haven't taken statistics yet, which is pretty much everybody, you may find that kind of, what do you mean it doesn't matter which 3 cards? Does it make a difference that does it really not matter that I always choose the first 3 cards to be flipped over? So we're going to both simulate it by flipping over the 3 cards, but I'll also show you that's the same as flipping over any 3 cards. Make sense? So we're just going to go with our original plan right now. Okay? So we generated our cards. We need to figure out what our choices are. Okay? So our draw is we flip over 3 cards. I'm going to call that our draw, right? Because we draw 3 cards. So we're going to grab 3 cards. And what is that? So I'm just going to simply say, hey, it's the first 3 cards. So cards from, and that's all I have to do. That's all I have to do to pick the first 3 cards, right? Do a slice from 0 to 3, right? I can leave it blank like this, but this will go grab index 1, index 2, index 3. Make sense? And now all I have to do is ask and then now I win if there's no reds in here, but I lose if there's red in here, right? So I'm going to type this out and then I'm going to delete it because I'm going to replace it with something a bit nicer. I'm going to first write an if-else statement. Don't bother trying to copy that down because I'm going to delete it and replace it with something a bit more efficient. So if draw, right? So let's see. If red not in draw. So I tried to make this as accessible as possible. I'm going to do the truth condition first. So I win if I don't draw a red card, right? That's my win condition. So if R not in draw. So if the letter R, meaning a red card, is not in the draw, meaning these first 3 cards, then I win. Return true. Else, return false. Okay? So that's what I said, don't bother copying down. I am going to simply just run this a few times to kind of show you. Print. What we're going to do is we're going to print our draw, just to kind of show you what a draw will look like. If red is not in draw, return true, else return false. So instead, what we're going to do is that we are going to do game, and it's going to print out both what we did, what our draw was, and whether or not we won or lost. Oh, and I forgot a semicolon. Oops. So not a full colon. Oops, that happens. Remember, you need a colon whenever you indent. It's hard to talk and type at the same time. So red, black, red. We drew both red cards there, right? I mean, technically you would stop after you drew the first one, but for the sake of figuring out whether something's random or not, you just For statistical purposes, you draw all 3 cards. Always. False, we lost. We won there, 3 black cards. False, 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 true, 1, 2, 3. Great. So we're getting random results. Great. So, okay, then this works. So let's simplify this a bit, okay? So how can I simplify this? So what we're doing here is kind of a classical thing you do basically at all levels of programming, and then you realize, wait, I can simplify this. Once you've been shown you can simplify this. What we're doing here is we're saying, if this condition is true, return true. Otherwise, return false. Make sense? If this condition is true, return true. Otherwise, return false. Okay? Or another way to put it, if the condition is true, return true. If the condition is false, return false. Or another way to put it, if this evaluates the true, return true. If it evaluates the false, return false. So I've said that as many different ways as I can. So what we can do here is, rather than doing that, we can just completely skip the if this else and just simply return that condition. Return R not in draw. This is a Boolean, right? I know that seems weird at first. It's also weird because I forgot to put the R in return. So let's fix that. So return R not in draw. Run it. And it's just a much more concise way of doing things. If you put either on the exam, guess what? I'm happy because you got the problem right. And I care about that more than about it being stylistic. Also, you have to make the question, is this more you have to answer the question, is this more readable for you? Or is this more readable for you? If this is more readable for you, then use this. Readability trumps that kind of thing 9 times out of 10. That 10th time is when you're actually worried about performant code, when you're actually worried about, hey, how well does my code perform? Does runtime actually matter? And the answer is, for your first couple classes, definitely not. Okay, so now we're going to go grab our statistics. So now, because we're just doing true and false here, since there are only 2 results, I'm not going to bother counting this with the dictionary. What I'm going to count is just the number of wins I get. So rather than creating a dictionary, right, like we did for the previous problem, wherever that is, yeah, right over here in the flip game, rather than creating a dictionary that stored all the outcomes because I wanted to see all the statistics of all the results, rather than doing that, I'm going to simply count the wins. That's what I care about. And in fact, on the exam, I mentioned, by the way, that this example I gave in class was the example that is the Monte Carlo problem I've used on the exam for the past year or so. So I'm going to need a new question. But even then, on the exam, I wasn't asking for the outcomes. I was asking for the wins versus, to calculate the win-loss ratio. So you didn't necessarily need the dictionary. That was kind of used as a bridge. So over here, since I'm counting the wins, all I need to do is keep track of 2 variables. Wins is equal to 0, which is how many times I've won, and then trials, which I put in all caps to denote something called a constant. That's just a stylistic thing. In other programming language, you have something called a final, like a final integer or a final double. It's the final countdown or something like that. So anyway, the point being is, what is a final variable? In other programming languages, it's a constant. It means you can't change it. Can't really do that so much in Python, but generally speaking, when somebody puts something in all caps, that means it's a constant, meaning don't change this thing unless you want to change, this is not a variable that's meant to be changed. We said it once. So we're going to play 10,000 of these games. So how do we do that? For in range trials. And then if game equals true, so if the game returns true, Again, this is one of those things that we can do a shortcut for. And so instead of saying if the game is equal to true, if the game returned true, we could just simply say if whatever that is true, right? But for a lot of you, this is probably easier to read. If the game is true, then increment the number of wins. Since I'm not bothering keeping track of the losses, so I don't need an else statement. Otherwise, I would keep track of the losses. The reason I don't need to keep track of the losses is because I can figure out the losses using some math. I can just simply say, if I want to count how often I lose, I just simply say trials minus wins. And that tells me how many times I lost, because I either won or lost. Make sense to everybody? You could just do some subtraction there. And that's it, I believe, unless I've missed something horribly wrong. So let's go ahead and see what the win ratio for us is. Wins divided by trials. That tells us how many times we won out of the maximum possible times we could have won. Okay, and so, and let's remove this print statement before I run, because otherwise I'm going to print out 10,000 of those, and that's going to take forever. So, run this. It says I won 28% of the time. 2 divided by 7. It's pretty darn close. So, when we calculate, when I went on the whiteboard, what did I say the win rate was? I said that the win rate was 5/7 times 4/6 times 3/5. The probability of each of those steps being done correctly multiplied against each other, which is 60 over 210, which simplified down to 2/7. So 2/7 is equal to 0.2857. And I got 0.2837. That's pretty close. This is the point when I say, like Monte Carlo, it's all about getting you close enough to that, right? You can say, okay, yeah, it's a 28% chance of winning. I don't need a 28.37 versus 28.57 to know that's a raw deal, right? That's where the power comes in. If I needed more precision, what do? I add more zeros. What do I mean by that? I add more zeros to the number of games I want to do. Because the more trials we do, the more accurate our result is going to be. So here if I do, how many was that? 1,000,000 trials. It's going to take longer. But here it gives me 28.60, which as you can see is closer to 20 is closer than 28.57. Right? Here. If we want it in terms of percentage, we can just simply multiply that by 100. If we want, and then you just mentally add a percent sign onto the end. Right, 28.6%. That's close. That's really close. That's close enough for us to use. It's close enough for us to say this is a raw deal. And what's nice is that it matched a known value. Right? So let's go ahead and pause. Resume Monte Hall paradox. So you will want to go to Runestone over here. So you want to go to Runestone directly. Go to runestone.academy and scroll all the way down to our exercises and go to exercise 12, the Monte Carlo simulation. Now, I'm going to be doing this well out of order. I'm not going to be doing this 3 parts. I'm not going to be doing the second part, and I'm doing the third part first, because they're completely independent exercises. Okay? Completely independent exercises from each other. In fact, they're so independent. Let's see. The Monte Hall, yeah, the video is currently unavailable. Whatever. This used to be an episode of Monte Hall. So Monte Hall is named after the Monte Hall challenge is a problem. It's famous. It's named after a game show presenter called Monte Hall, who had a game show called Let's Make a Deal. And behind it is our and what it was is that it would cap off with a game. Okay. Monte Hall problem. It's famous enough on Wikipedia. Okay. So the idea here behind the Monte Hall problem is as follows. Okay. behind me are 3 doors, and I'm the game show host, so I know what's behind the 3 doors, okay? Now, behind one of those doors is a new car, and behind the other 2 doors is a goat. Now, because I am married to a person who works at a zoo, I need to emphasize that the goats are considered less valuable than the car. The car is considered more valuable. You want to win the car. My wife really likes goats. So she works at the Philadelphia Zoo with the goats a lot. So good job. It's a really fun job for her. Anyway, so behind one of these is a new car. Behind 2 of these is a goat or some other thing that is not useful, but it's typically a goat because that's funny, to be honest. I mean, personally, I would just listen for the noises, to see which door you would want to open, but let's assume you can't, okay? So here's the thing. Here's the way the game works. You choose one of the 3 doors, okay? You choose one of the 3 doors, and then this is the fun part. I will open up a door, and I'll show you that there's a goat behind one of the 2 doors you didn't pick, right? So suppose you chose door number 1. I'll go to door number 3 and say, here's a goat. Do you want to switch? Do you want to switch to door number 2, or are you going to stay with door number 1? So the question is, stay or switch? Any volunteers? Yes.
Switch, because then if you know that the door that has a goat is not a car, that means that that other door has a 2/3 chance of being a car, and the door that you originally picked was only a 1/3 chance.
Correct. 100% correct. The answer is switch. The answer is always switch. That gives you a higher probability of winning. But what you may not have heard, what you may not have picked up on was the probability of winning. So if you switch, what do you think the probability of winning is going to be, just instinctively? Right? Instinctively, you're going, well, there's 2 doors now. If I switch, now it's a 50-50 shot of winning, right? So I've got a 50-50 shot. That's wrong, though. If you switch, you now have a 66% chance of winning, because it's not just a door. It's not just choosing between one of 2 doors. You're switching between one of 2 doors that originally had a 1/3 chance, given that you know what is behind another door. This is called Bayesian probabilities. Or Bayesian statistics. It's wonderful. Now, this became a very famous problem in 1990 because of a column in Parade magazine called Ask Marilyn, which was where people would ask Marilyn Vosavant, a very smart woman, hey, here's a question for you. Can you answer it for me? And so this was the original way the game was phrased, and she responded basically correctly saying, hey, you should switch. By using the assumptions you have laid out in the problem, it is a 2/3 chance of winning if you switch, a 1/3 chance of winning if you stay. I'll explain that how we got there in a couple of different ways, because I know that a lot of you are going, huh? Okay. Now, what was extremely interesting was the complete and utter reaction to Vosavant's column. After the problem appeared in Parade magazine, approximately 10,000 readers, including nearly 1,000 with PhDs, although I don't know if they had math PhDs or related fields or not, wrote to the magazine, most of them saying that Vosavant was wrong. So and it says here, even when given explanations, simulations, formal mathematical proofs, many people did still not accept that switching is the best strategy. I can't put a finger on why they would want to tell her she was wrong. Can't put a finger on that. Anyway, but Paul Erdos is one of the most prolific mathematicians, and even he was unconvinced until he was shown a computer simulation. Paul Erdos, by the way, and just so you understand this, okay, do you understand what a Bacon number is? Like Kevin Bacon? So that is, your Bacon number is something you, if you're an actor or an actress, you keep track of. It is your degree of separation from Kevin Bacon. A Bacon number of 0 means you're Kevin Bacon. A Bacon number of 1 means you've acted with Kevin Bacon. And a Bacon number of 2 means you've acted with somebody who acted with Kevin Bacon. And a Bacon number of 3 means you've acted with somebody with a Bacon number of 2. Mathematicians use an Erdos number kind of for bragging rights, and my Erdos number is 5, as it turns out. So I've published a paper with somebody who has an Erdos number of 4. This sounds impressive, but it's actually kind of the mean Erdos number for anybody who's keep track. This is what most people get. So anyway, so he had to be shown a computer simulation to show this was correct, and Erdos was one of the best. So if you're feeling confused, don't worry. There's plenty of other very smart people who were confused by this. Now, why is it always better to switch? So here's the kind of assumptions that we need to work on the problem to make sure that it works. The host always opens something you don't select. So if I'm opening door number 1, he's not going to open door number 1. That would just be silly, right? Because now I have to switch, and now it's just silly. Okay? The host always reveals a goat and not a car, because if you choose door number 1 and I reveal a car and say, do you want to switch? Well, both of those have a goat now, so there's no point in switching, right? And I always offer the chance to switch the door, right? Okay? So let's just kind of look at this one. Example over here, some simple solutions of this. Right? There's 3, so basically there's and the reason this works is because rather than thinking of it in this traditional kind of probability, let's just kind of look at the examples. Right? Let's suppose I always choose door number 1. Okay? If I choose door number 1 and the car is in the 3rd position, if I switch, I win the car. If the car is in the 2nd position and I switch, I win. But if the car is in the 1st position, I have to stay to win. If I switch, I lose. So that's so the car can be in one of 3 different places, right? And if I switch, I only lose if I chose the car first. So let's go ahead and kind of absurdify this example. Suppose I have 1,000,000 doors, and there's 999,999 goats. Oh boy, does that stink, what a smell that is, and there's 1 car, okay? I am going to go ahead and choose a door. Okay, I'm going to go and choose door number 1, okay? Now, I have a 1 in a million chance of getting that right off the bat, but as you well know if you read any Terry Pratchett, 1 in a million and 1 chances happen 9 times out of 10. So, anyway. So, I have a 1,000,000 and 1 chance of getting that right. The issue is, of course, is now what is he going to do? He's going to open doors. But he's not just going to open 1 door. He's going to open 999,998 doors. So we're left with the same kind of choice that we have to make in the original problem. So he reveals 9,999, 998 goats. So the question is, do you think you got that car on the correct on the first choice? No, he had a 1 in a million chance of getting that right, so I'm going to switch because that seems like really good odds there. Okay, so that's kind of the example I like to give there. That's how it worked for my brain, at least. And you can go through this Wikipedia page, and it shows, okay, this is how you use conditional probability, right? So right, so this is the probability of every single outcome if you pick door number 1, right? If you pick door number 1 so we're always going to pick door number 1 because it doesn't matter which one we pick, really. We're going to pick door number 1. If the car's under door number 1, host will either open door 2 or 3. If I stay, I win. If I switch, I get a goat. So that's a 6 probability, and that's a 6 probability. Then if the car was originally under door number 2, the door and I've chosen door number 1, then the host has to open door number 3. That has a 1/3 probability chance of happening, so if I switch, I win. And then for 3, he'll open 2, right? So again, though, what we're going to do is instead we're going to simulate this game, because that is the way we can kind of do this. Because, again, statistics are hard because this is counterintuitive. It is counterintuitive because most of us, when presented with a problem, think it's a 50% chance of winning. So it actually doesn't matter if we stay or switch. Okay? But it does matter. So let's go ahead and take a look. So game, let's go ahead and make a new, I'm going to make a new function in here. I'm just going to call it goat game. Greatest of all time game, all right? Goat game. And what we're going to do here is we are going to, we need to set up our doors, right? So we are going to use, let's see, so we need our doors is equal to, and let's go ahead and actually spell things out. Goat, because we've got the space for it. Goat, goat, and car, right? So we've got our 3 things, and now we need to make sure that this is randomly generated, right? We have to make sure that we have a randomly arrangement of goat versus car, right? So the car has to end up somewhere at random. So we know how to do this now, though. We use random.shuffle, right? Random.shuffle to change where this is. I forgot to do random.sample. I'll go back to that in a bit. Random.shuffle. Doors. Cool. So now that's going to shuffle around the goats and the cars. Like we can see, and we could probably check, we could do this as goat 1, goat 2. In fact, we can. Goat 1, goat 2, car, I think. If not, oh well. So we're always going to pick, let's go ahead and say we're going to pick door number 0 as our solution, as what we have. Pick is equal to 0 if, and so there's 2 probabilities, there's 2 possibilities, not probabilities because they're not equally likely. There's 2 possibilities, okay? If pick 0, pick from doors dot pick. Yeah, there's no need for pick. If doors 0 is equal to goat 1 or door 0 equal to it doesn't matter. We could have just simply said if they could have been identical goats, it doesn't really matter. Okay, but if we chose either goat, right? If we found goat 1, he's gonna. Let's go ahead and actually, you know what? I'll break this down even further just to make sure we're explicit. If goat 1, if doors, so if goat 1 print door and then doors dot find goat 2 I mean, this is if I want to go into real detail about it. Normally I don't go into this level of detail, but why not? And then otherwise, if we found goat 1, doors, goat, car. I'm going to rewrite this and oversimplify it because guess what? Just trying things out and trashing them is a perfectly fine way to do things. And then I'll just simply copy this. As goat. So now the other thing I'll do over here is I'll say switch. So I'm going to change this. So one thing I want to do over here is kind of just be able to do this experimentally, right? Which is that I'm going to show, okay, what's going to happen. Am I going to switch or do I stay, right? Which one is better? So if I reveal goat 2, so we reveal goat 2, I'm going to go ahead and return switch. If I'm switching, then that's going to win because I revealed a goat, I'm going to switch away, and if I switch away from goat 1, that's going to win. If I originally pick goat 2 and I switch away, then I'm going to win. But if I originally picked a car and I switch away, I'm going to lose. I know, it seems rather simplistic over here. And we honestly don't need any of those print statements to work over here. So now let's go ahead and go and do trials, where I'm going to change this out. It's the same. So notice that this is barely going to change. Wins is equal to 0. We're going to do 10,000 trials. For how many trials are we going to do? And we're going to simply do goat game instead of game. Goat game is equal to switch. I'm sorry, not switch, but true, because we want to try switching, and then we run it. And it says, hey, look at that. You have a 66% chance of winning. We can go into more detail about this if we want to, but if I try to switch away, right, then I have only a 33% chance of winning. Okay, yes? Switch is just simply up here, like that. Oops, sorry. It is part of this. Oh, sorry. Give me a second. Why am I doing it in here? So take what you have, take all this nonsense that you have, copy it, and dump it into, we were doing this, this was a runestone problem, completely forgot about that. So take it, and we want to dump it onto runestone, which is not the stock problem one, but over here. Yeah. Save and run. And then, oh yeah, I forgot to import random. Import random, save and run. And now I'm going to go ahead and switch this. Sorry, I'm going to share the code with everybody. Okay, cool. Well, no, we're only going to be doing the first section and the third, and this very last one.
Oh, okay.
We're only doing this block and the other block. So there's a lot of cases where statistics can seem counterintuitive, and it mentions that this is that Monte Carlo is kind of that kind of case. It's a paradox of the vertical type, because the Sentinel solution is so counterintuitive it can seem absurd, even though it's true. Although personally, after having done this 1.5 million times, I don't see how it could be anything but. All right. So now we are going to throw back to something we did very early on into the semester, which was we did approximation of pi. Remember this formula? Pi over 4 is equal to 1 over 1 minus 1/3 plus a fifth minus a seventh plus a ninth, right? Where we did an alternating sum of fractional units, right? Remember this? and that it is eventually hit pi over 4. All right? Personally, though, the authors say that they find the Monte Carlo simulation is more fun and a lot more intuitive to understand. I don't necessarily know if it's more intuitive to understand, but it's certainly a heck of a lot more fun. Okay? So suppose it's saying that we've got a unit circle. Let's see, is it a unit circle? Yes. Suppose we've got a dart. So here I'm going to need to do some geometry because the question requires us to look at some geometry, but it's very basic geometry, okay? Okay. Suppose I have a magic dartboard, okay? It's composed of 2 parts. We've got, let's use the pretty one. Actually, hold on. I can do better than this. I can tell it to draw a shape. Suppose I have a magic dartboard. Okay. Okay, and the dartboard is consists of 2 parts. The circle that you throw the darts onto, and sorry, this is going to it is tricky to do this and line it up correctly. Oopsie. Okay, that seems good. No, detach them. Here we go. Oh, okay, that's close enough. Okay, because I want to get them to touch. There we go. Okay, that's close enough. So I've got this dartboard over here. Okay. Okay, yeah. So I've got this dartboard here, and it consists of 2 parts. The dartboard, where you throw it at the dart, and if you land it in here, you get a point. And then you've got the board the wooden board that it's on. Okay. Now this is a magical dartboard, so anything I throw, even if I throw it in the opposite direction, it's going to go and hit the dartboard. Okay. It's going to hit either the square. It's going to hit somewhere inside this square, be it in the circle or be it in that square. Make sense? It's either going to be in that circle or outside of it, but it's going to land in this. Okay? Believe it or not, we're going to use this to calculate pi. So how? So the idea here is that I've got this unit circle. Let this be a unit circle. What does that mean? For it to be a unit circle means that the radius of this thing is 1, right? That's what a unit circle means. It's a radius of 1, which also means that this over here is 1. So again, this is a unit circle, and this circle fits in perfectly inside the square. So that means that this goes up to over here. That's 1. This is also a distance of 1, right? Which means that the side of the square is how long? 2, exactly. That this is too long, okay? All right, so this is too long. So let's use some just geometry that we know about this. So let's talk. So what is the full area of the circle? What is the area of the circle? The circle's area is what? 1/2 pi. Was it pi r squared? Right? Pi r squared. Pi r squared, not 1/2. What's 1/2? There is no 1/2. I'm being silly. Pi r squared, right? Yeah. I said, why am I saying 1/2? It's not. It's pi r squared. Pi r squared. Okay. So the math here is fairly easy, which is if I want to know what this is, I take the radius and square it. What the radius of 1 squared is 1. So the total area of this circle is pi, right? That's the total area. Next, let's look at the square itself. The total area of the square is the side squared, right? The area of the square is s squared. That looks like a 3. It's not cubed. Side squared. So 2 squared is what? 4. So this says that we've got see, pi over. So actually, it's less of a division, but more if it's a. Let's write it down as a ratio instead. Pi to 4, right? We've got pi. So we've got this circle over here inside the square that is made up of pi area, and the total area of the square is 4, right? 4 units squared. So here's the thing. The idea here is that if you throw darts at random at this dartboard, okay? If we throw darts at random at this dartboard, it's going to land somewhere in this, okay? The probability that it lands inside this circle is pi over 4. Why? Why? Because this makes up 3.1415 out of 4 of the total amount of area in there, okay? And the probability it doesn't land in there is 4 minus pi over 4. The probability that doesn't land in there is basically the probability it lands in here instead. Make sense? So what we could do is that we could randomly throw darts at this dartboard, okay, and keep track of the number of hits to the total number thrown. And the more that we do this, the closer it's going to approximate pi over 4. The closer it should get to this ratio. Make sense? So, let's actually throw some darts, so to speak. Now, how are we going to do that? We're going to do that with turtle. Okay? So, let's see. Let's start with the animation part before we do too much math. So before this, let's go ahead and set this up. We need this to be something that makes sense. I want it to take place inside a unit circle. So, which means that if I want this point to be 0, 0, that means that this corner needs to be 1, 1, and this corner needs to be -1, -1, right? Right? So, I believe that is, so if I look at turtle graphics, okay, set coordinates, okay, set world coordinates. So let's see. It says, hey, give me the lower. It says just give me these the lower left x, lower left y, upper right x, upper right y. And what it's going to do is that it's going to turn basically the screen, the coordinates of the screen to just simply, the window that pops up just to be that small area from basically just be this board. Okay. So let's see if I can't do that. Import turtle. How do I do this? Turtle dot. Let's see. How do I get the screen? Turtle dot get screen. I think it is. Does it just get screen, or do I have to use? Okay, let's go ahead and minimize this. Right, turtle dot get screen. No. Sorry, this is the one part that I forget how to do each time. Win coordinates. World coordinates. Okay, yeah, it is screen. I don't know why I keep alt-tabbing when that is the incorrect thing to do. It should be just simply get screen. S is equal to that. S dot set world coordinates. And what it asks for is a -1. It asks for the lower left corner. What is going to be the lower left coordinate? and what's going to be the upper right coordinate, because, which is going to be -1, -1, right? Because the center of the screen is going to be 0, 0. -1, -1 over here, and then 1 and 1 for the other parts. Save and run. Let's see, did it work? Okay. Now we have to test this. We're going to test this by saying t dot, we're going to go and say Bob is equal to turtle.turtle. By the way, I got an email today from somebody asking, hey, are turtles going to be on exam 2? No, they're not. Turtles are not going to be on exam 2. Turtle.turtle. Okay. And we're going to say Bob.goto 1, 1. And notice that when I told him to go to 1, 1, look where he ended up. Okay. I think what I need to do instead, let's see. Ooh, I know what I need to do instead. Okay. I think instead of doing turtle, will this work? Bob, so I don't end up with an extra turtle. Yes, that worked. Okay, so it should be Bob is equal to turtle.turtle. Get Bob's screen, which is S. Tell it to set the world's coordinates of that screen to be 1, 1. And then I tell him to go to 1, 1. So notice that the corner now is 1, 1, as opposed to if I didn't have this, telling him to go to 1, 1 would just tell him to move barely anything at all, because that's just a pixel, right? And this is great. This is part of what makes the turtle module really great, because you can do that, and then I can tell him to go to 1/2 x, and then y is equal to 1, and then it does do that. That's awesome. Okay, so now we are going to abuse Bob by throwing him at the screen a whole lot. Poor Bob. We're going to say Bob dot set shape. I think it's set shape is equal to turtle. I forget. And is that how we do it? Turtle. Is it set shape? What is it? No. What is? It's just shape. See, I always forget these things, even though I did them like last week. It's the issue with having to remember these things like off the top of your head. There we go. So we've got him. Awesome. And now, Bob.shape, boom. We have him there. And now we just need to, what we need to do is that we need to generate a dart throw. In other words, we need to generate to throw the dart. I said if we throw a dart, it's always going to land in this square somewhere. That means that we need a random x value between -1 and 1, and we need a random y value between -1 and 1. Okay? Now, if we go ahead and look at the random module, just again, right? I think it's Control F uniform. Gives us a random. This is what we need for randomness. Most of the time, when you use randomness, you're going to use random.choice, by the way, to choose something. Or random.randint, to choose a random number. Random.uniform is how you get a random float between two values. So here, if we do random.uniform, this is going to give us a value between A and B, whatever A and B are. So if I tell Bob, so if I do random, so here I've got to import random as well. Import random. I am going to need the entirety of the course time here, of this class time. So, and please stay. It is worth it. Random.uniform. -1, 1. So let's see. So if I generate a random x and a random y, okay, we can test this out by telling Bob.goto that random x and y. Make sense? So here, what did I mess up? Error float has no attribute y. Oh. There we go. See, even I make these kind of mistakes. So it's randomly generating this. So what we need to do now is we are going to use this to generate a random thing. So what we're going to do is we're going to write a function, def toss, or throw. This will basically throw Bob at a specific point, okay? Also, let's go ahead and tell you Bob.pen up, because we don't need that right now. So to throw Bob, we need that X and we need that Y, and we'll worry about graphing him later, okay? Or just a second. Yeah. Actually, let's go ahead and just do that. And then he'll go to that position and then Bob.stamp. Okay? And then trials. We're going to just do this like we always did it. Trials is equal to 10,000. I'm actually going to do 100 here because we'll need to speed it up. For in range, trials, throw Bob. And so here we go. Bob's just getting thrown to random places. Now we don't know whether or not this is a hit or not, right? So we're going to have to write the code to figure that out. The other thing we need to do is we're going to use tracer. Just a second to speed this the heck up. Tracer. Set turtle.tracer and what it does is that this will accelerate this. So what we're going to do is we're going to just go ahead and grab what's over here, the 825 from that. Okay. Okay, Bob dot speed 0, Bob dot tracer 8,25, and this should greatly speed things up. See, it went much quicker after that. So now we need to figure out. Let's go ahead and put this on to 10,000. It's probably not enough for the tracer. What we need to do is delay only the. Let's go ahead and do 100. Okay, but as we can see, we're filling up the board with Bob. Okay, but now we need to do something useful. We need to figure out whether or not this is a hit or not, and we got to figure out whether this is approximating pi. So what are we going to do? We have to use. So we need to know whether it lands in the circle. Now the circle, as we know, is a unit circle, which means that it's inside the circle. It means that it's within one of the radius, right? It's one away from the center. So what we have to do is figure out how far away it is from the center. To do this, we use the distance formula, the Euclidean distance formula, which you've learned at some point and are like, oh, how does that go again? No, it's the one where you take the square root of the thing squared, right? That's the one we're thinking of. It's the square root of the thing squared to figure out how far it is from the distance. So, import math. Don't you hate having to do that? I promise this is worth it. Okay, distance is equal to math.squirt of x squared plus y squared. Right, the square root of the x squared plus y squared. That's Euclidean distance there. Okay, that gives us a number, and if that is, and then we're going to say if dist is less than, or let's go ahead and say hit is equal to true. We're going to assume it's true for a second. If dist is less than or equal to 1, then we are going to say that was a hit. Hit is equal to true. I mean, we already said that, but whatever. And then we're going to also say that bob.color is blue. Else hit equals false. Bob dot color is equal to red. Then he'll just move to that spot and he'll stamp. So if it's inside the circle, be blue, otherwise you're red. And look at that. So hit is assigned a local variable and not used. So what we did here is I just simply told him, hey, if you land in, if the distance from the center of the circle is 1 or less, using that formula, which I know off the top of my head because I've had to use it 1.5 million times, so don't worry about the fact that you don't remember it from whatever math course you took. I literally had to use that a lot. And then I had to mess with distances that don't make sense. But let's go ahead and see. Does this tell us anything useful? Well, okay. So we throw Bob and we were returning, and let's go ahead and say, and we had a hit. So let's go ahead and return hit now. And then what I'm going to do with that is I'm going to say hits is equal to 0 if throw Bob equals true, right? If we got a hit, hits plus equals 1, hits, and then finally print hits divided by trials. This should be close to pi over 4. So what we're going to do is multiply this by 4 to get our value. Times 4. And now let's see, after we do 10,000 of these things. I'm going to save and run this, and then I'm going to share it with you. What do you mean local variable hit is assigned but never used? Line 23. Yep. And look at that. The value we got, 3.1424. It's not like the other approximations we've done in the past. It's not a great approximation, but it gets to pi. It gets there the more you do it. So I'm going to share this one with you. As you can see, you can use Monte Carlo approximations to basically approximate a lot of things just by using randomness. So again, I'll talk about this on so the plan is I'll talk some more about, I'm going to talk about the project on Tuesday, okay? Oh, and before I forget, because I did say I was going to go back to that, back to this one for a second. If you try this instead, in the code random.sample cards, it will come out with the same thing. Okay, so that was all I wanted to go over with that one. All right, have a great weekend.